In my mind, one of the strongest early life claims comes from volcanic glass in South Africa. On its face, it seems like an unlikely place to have any fossils. After all, volcanic rocks are erupted at thousands of degrees of temperature. So how can they have fossils in them? Well, it turns out that modern volcanic glass, particularly glassy rims of pillow lavas erupted on the sea floor, are colonized by all kinds of microbes after they erupt. These microbes tunnel through the volcanic glass, hunting for metal cations that they can metabolize, that they can literally eat. Furness et al., 2004, report microbial borings in pillow basalt glass from Barberton, South Africa. The pillow basalts date to 3.482 billion years old based on zircons, and have been further dated using cherts overlying the lavas that are 3.47 billion years old. The borings in the glass include very distinctive morphologies, from spiral tubes to clumps to straight tubes interrupted by knobby holes, and so forth. The borings are suggestive of thermophillic life in hydrothermal systems. Thermophiles are organisms that like water greater than 70 degrees centigrade. The nature of these organisms has not been determined. Now, similar traces are found in modern basalts, and basalts, in fact, of all ages, to a depth of several hundred meters below the sea floor. The presence of modern analogs makes a strong case that the Archean ones are remnants of actual life. It seems there were thermophilic microbes in the deep biosphere already about as old as we have a rock record. There are other claims for very old life as well. For instance, Alwood et al. 2006 report 3.465 billion year old stromatolites from the so-called Strelley Pool cherts in the Pilbara of Australia. These are laminated sediments that have been described as stromatolites created by consortia of prokaryotic bacteria. But these have also been disputed on the grounds that such structures can form inorganically. For instance, Lowe et al. 1994 argues that these stromatolites are inorganic because they are rare, they have no sediment between the mounds, they have uniform laminae thickness, and they're associated with evaporites. And also in one case, they show evidence of mechanical folding, suggesting that the stromatolite was well cemented before it was deformed. Now, others have examined the same area and found additional stromatolites that Lowe did not look at. So these contain several orders of contorted laminae. They have kerogen-rich laminae, which suggest organic material, and they have lenses of desiccated fragments of layers from the stromatolites that fill troughs in between the different mounds and are unlikely to reflect hydrothermal activity or post-depositional folding. Nobody so far has reported filaments or microbial cells from these structures. Now, Alwood et al. 2006 note also that these stromatolites show a diversity of shapes, from conical to mound-like to cuspate and so-called egg carton-like forms. They also show evidence of being soft and therefore not abiotic crusts. And in addition, I think most important of all, they have a lot of morphological diversity where that diversity is distinctive of different depositional environments, from mudflats to shallow marine, like inner shelf kinds of settings. And so that evidence of diversity of morphologies suggests different kinds of communities living in different environments.